In this video, we're going to talk about confidence intervals. We need to go through some definitions first. The first definition is what we consider a point estimate. A point estimate is a specific numeric value that estimates that of a parameter. In other words, the parameters, remember, are those values of a population. Most of the time we don't have the population, we have samples. And so we want to know what the best estimate for a parameter is, and that is a point estimate. So for example, the sample mean is the best point estimate of the population mean. So the sample value of whatever you're looking at is the best point estimate of the population value that you're looking at. Again, we're just looking at estimates on these. Interval estimate is just a range of values used to estimate that parameter, because again, when you're looking at samples, they're not going to be exact values, because we can't have something that exactly equals the population. We can have it approximate the population, but we don't know exactly what the population is because we don't have the population itself. We just have a small sampling of it. Our next definition is a confidence level. A confidence level is the probability that a parameter lies within a specific interval estimate of the parameter. Just meaning, how confident are we that it's going to be within this interval? The confidence interval is the specific interval estimate of a parameter determined by using data obtained from a sample and a specific confidence level of the estimate. We have common intervals that we're going to be using, and those confidence intervals are going to be the 90% confidence interval, the 95% confidence interval, and the 99% confidence interval. These are the three most commonly used confidence intervals that we use. You can use others, but these are the most common ones that we tend to use. A couple of things that we need to look at is, how do we find confidence intervals? The formula for finding confidence intervals: when we know the population standard deviation. We have to make sure that we know the population standard deviation for this particular case. If we know the population standard deviation, we're going to be using z-scores. Now then, z-score, this symbol right here, what it is z alpha divided by 2. Your alpha is the value that is in the small tail here. The alpha goes, what we say alpha divided by 2 is in here. If we're looking at, say, a 90% confidence interval, 90% is in the center here. We're 90% sure that it's in here. So that means 10% of it is left over. We divide it by 2 because we have two tails. We want the middle 90%. So we divide it by 2, leaving us with 0.5, because we have 0.10 divided by 2. And so we have 0.5. So the alpha is the amount left over from our confidence interval that we're looking at. So that is what this right here signifies is the amount in each part of the tail. And it's important because if we're not given the specific confidence interval, such as our three most common ones, we need to know this when we're going to be looking them up in the z-score table. Now this is the formula that we use when we're finding confidence intervals. Your mu, we do not know. That is what we're estimating. So this never changes when we're finding confidence intervals. We will be given or can find all of this information and simplify these two items down to single numbers. This will stay the same because an interval means that the population mean is between two numbers. Now then, the three most common confidence intervals that we're going to use, again, are the 90%, the 95, and the 99. And I give you the z-scores for both of those. 1.65, 1.96, and 2.58. There will be others that we can use, and we'll get into how we can use those and everything in a few moments. But let's look at something else, which is considered the margin of error. This is the maximum likely difference between the point estimate of a parameter and the actual value of the parameter. This is just what is the difference? How much do we add or subtract on? The margin of error is considered E. E is our z alpha divided by 2 times the standard deviation divided by the square root of n. Now if we look back at our previous slide, right here, this is E. Okay. So I can rewrite my confidence intervals as x bar minus E less than mu less than x bar plus E. So E is what we add and subtract on. It's that plus or minus portion that we're looking at. We take our sample mean and we add or subtract a little bit. It's that buffer zone. How confident do we want to be in our numbers? You have probably seen at some point, like on presidential elections, things like that, when they're talking about polling, you'll see that their approval rating or the polls are 64%, and then you'll see this little bitty plus or minus 0.2%. Well, this 0.2% is your E. It's your margin of error. It's that little buffer zone, meaning they don't have the entire population. It's an estimate. It's a confidence interval. They have estimated what the population agrees to. That's what they're looking at. And that's what we're looking at here also. Rounding rules for confidence intervals, we're going to round to one more decimal place than the original data, which means whatever our sample mean is in, that is what our final answer is going to be in. Because remember, your sample mean is already rounded to one place more than your original data is. So whatever your sample mean starts out to be, that's what your final answers need to be in as well. So let's look at an example. We have a random sample of 50 cars in the drive-thru of a popular fast food restaurant, revealed an average bill of $18.21 per car. The population standard deviation is $5.92. Estimate the bill for all cars from the drive-thru with 95% confidence. So let's first start out by writing down the information that we know. A random sample of 50. Well, that tells me n is equal to 50. Then it says that of this random sample, the average bill was $18.21. So since it was from the random sample, that means that the sample mean is $18.21. The population standard deviation is $5.92. So we have sigma is $5.92. And we want a confidence interval of 95%. So that means that our alpha is equal to 1 minus 0.95. So if alpha is 0.05, that's how we get our alpha. Now I've already given you the values that we're going to use when we have a 95% confidence interval, and that z for alpha divided by 2 was 1.96 for a 95% confidence level. We're going to use the formula x bar minus z alpha divided by 2 times sigma divided by the square root of n is less than mu less than x bar plus z alpha divided by 2 times sigma divided by the square root of n. And now I'm going to plug in my numbers that I have. I have 18.21 minus 1.96 times 5.92 divided by the square root of 50. And again, I do not change mu. Mu stays the exact same. And over here, it looks the exact same except for my minus sign changes to a plus sign. And that should be 1.96. It's 5.92 divided by the square root of 50. Okay. Now if I solve this portion right here, 1.96 times 5.92 divided by the square root of 50, if you'll notice that your sample mean is in 2 decimal places, so I'm going to go ahead and round my answer here to 2 decimal places, and that's going to be 1.64. 18.21, and it's going to be the exact same number over here. So I'm going to take 18.21 minus 1.64, and I get 16.57 is less than mu greater than 18.21 plus 1.64, which is 19.85. Our last part is to write this in a statement in which it applies back to our problem, which was going to look like the mean bill for all cars, and the reason why I say all cars is because we're estimating for the population from the drive-through at this fast food restaurant is between $16.57 and $19.85. This is with a 95% confidence. Notice I said we were talking about the mean bill for all cars, and then I described that it was for the drive-through of this fast food restaurant. Then I said it was between what numbers, and I also gave the confidence level that we were looking at. These are very important items to have in your conclusion of the statement. Sometimes you will not be given one of the three major Z values or the three major confidence levels. Sometimes you'll be given something else. So what we're going to do is trying to find your Z value given other confidence levels. So if I want to do that, I'm going to follow these 4 steps. And what that is I'm first going to subtract the confidence level from 1, which is going to give me alpha, just like I did earlier. It's 1 minus my confidence level. Just like I did earlier with 1 minus the 95% and gave me 0.05, that gives me my alpha. Then I'll divide it by 2, because remember, confidence levels have both tails in them. I'll draw a normal curve and put the alpha divided by 2 in each tail. So alpha divided by 2 in each of the tails. Then I find the Z value that corresponds to this alpha divided by 2. The key here is I always want to use the absolute value. So always use the absolute value of the Z that you find. And the reason why is the positive and negative values of these Z's already is put in there for the confidence intervals inside the formula when you have the plus and minus of the actual margin of error. So those are already taken into account. Okay? So let's look at an example. Find the Z that corresponds for an 88% confidence interval. So this is not one of our major 3. So the first thing, 88% is the same thing as 0.88. So that means that alpha is equal to 1 minus 0.88. So alpha is equal to 0.12. That is going to be the alpha that we're looking at. Since we're looking for a confidence interval, that means that I have to divide it by 2. So alpha divided by 2, which is 0.12 divided by 2, gives me 0.06. So that means that 0.06 is in each of the tails. And I'm going to go ahead and add on 2 more zeros, because remember, in the center of our table our probabilities are given to 4 decimal places. And I want to find the Z's that correspond to this. Well, what I'm going to do is I'm going to come down to the table, and remember that we're looking for a Z of 0.0600. That's less than 0.05. So I'm going to be looking in the negative side of it. So 0.06. So 0.06. Here's 0.01. Okay, here's 0.05. Here's a 0.06. 0.06, 0.06, 0.061, 0.0606. Okay, right here. Notice it is between these two numbers. And we want to go to the one that it is closest to. Here's the thing. It is exactly halfway between these two. If it is halfway between the two, go to the one on the left. So go to closest or one on the left. So we're going to go to the one on the left if it's exactly halfway between. If there's one closest, always go to the closest. Otherwise, go to the one on the left. Then we're going to follow that out, and I get negative 1.55. So the z that I'm going to be using, again, use the absolute value, is 1.55. Because remember, when I put this into my formula, it takes into account the positive and the negative as far as my margin of error. Okay? You'll want to practice some of these, finding out the different z's for different confidence levels. One other thing that we want to look at is, what if we want to find the sample size? The minimum sample size needed for an interval estimate of the population mean. We know how accurate we want to be. In other words, we want to, we already know our margin of error that we want. So we want to know, how large of a sample do we have to have in that case? One key thing here is, for sample size, you always have to have a whole number. Always have a whole number, and you always round up to the next number, up to the very next whole number. So if you get any type of decimal or anything like that, you always round up to the next whole number. This is the formula that we're going to be using. And remember that the E is your margin of error. Key things here is E represents if it says accurate within, or if it says just within. These are the key phrases that you're going to be looking for to pull out your E value, okay, to put into this formula. So let's look at an example. It is desired to estimate the mean GPA of each undergraduate class at a large university. How large of a sample, forgot my P there, is necessary to estimate the GPA within 0.25 at a 99% confidence level? Population standard deviation is 1.2. Okay, so how large of a sample? So that means we want to know N. To estimate the GPA within, that is our E, 0.25. A 99% confidence level, and I gave you this value previously, so that is 2.58. And the population standard deviation is 1.2. So that means that if we plug these in to our formula, n is equal to our z, which is 2.58, times your standard deviation, which is 1.2, divided by your margin of error, which is 0.25, that amount squared. Make sure that you solve everything inside before you square it. Wait till the very end to square it. So 2.58 times 1.2 gives me 3.096 divided by 0.25. And I'm going to scoot this down just a little bit. Divided by 0.25 gives me 12.384. And then square that, and I get 153.363. But I can't have part of a person. And here's the thing. Normal rounding rules would tell me to round that down to 153. But the problem is if I round it down to 153, I actually will not have enough for the error, margin of error that I'm wanting. So I want to always round up. Therefore, the n that I'm looking for is 154. Because I want to be accurate within a certain amount, that is the key. I always want to round up. Then I want to draw my conclusion and apply it back to my problem. So a sample size of 154 undergraduate classes is needed to estimate the GPA within 0.25 at the 99% confidence level. Notice again, I included the confidence level, I included the margin of error that we're looking at, and I included something about what we were looking at, the GPA and everything. Make sure that you give those details. Be very detail oriented and apply it back to the actual problem when you're drawing these conclusions. Practice some of these, ask questions, and if you need help, let me know.